Hello one and all, welcome to another online video by Einstein Academy. In this video, we'll be looking at learning outcomes F and G from the topic of chemical bonding from the JCH2 chemistry syllabus. Learning outcome F, candidates should be able to explain and deduce bond polarity using the concept of electronegativity, while G is to be able to deduce the polarity of a molecule using bond polarity and its molecular shape. So we're going to be also using part of the knowledge whereby we use the VSEPR theory to deduce the shape of a molecule and combine it with what we're going to learn about bond polarity in this section to be able to deduce the overall polarity of a molecule. So let's begin. Okay, so the first thing that we need to talk about is covalent bond with ionic character. So let me do a brief review. As in previously, when we studied ionic bonds, we said that ionic bonds can have covalent character. So for example, in the case of AlCl3, okay, when Al will transfer 3 electrons, one each to each chlorine atom, and then in doing so, it will form the Al3 plus cation ion, and then you have the Cl minus N ion. And because of the fact that the Al3 plus has very high charge density, and because it's positively charged, it will actually start to draw back some of the electrons from the Cl minus ions. And because Al3 plus is such a high charge density cation, this effect is so large that eventually it ends up that AlCl3 actually shares their electron instead of it being an ionic bond. And AlCl3 is a covalent compound, which is the most extreme form of an ionic bond with covalent character. Okay, so previously we actually studied that ionic bonds can have covalent character. In fact, all ionic bonds have covalent character because when the metal forms the cation, it will always attract some of the electrons back from the N ion just because of the fact that it's positively charged, and it will attract the electron cloud of the N ion. That is ionic bond with covalent character. Today we're going to talk about covalent bond with ionic character. So some covalent bonds can have ionic character. So in covalent bond, atoms with few valence electrons in the valence quantum shell can share their valence electrons to obtain stable noble gas electronic configuration. That's the reason why they form covalent bond. The electrons is supposedly shared equally between the atoms. However, because in the covalent bond, right, it can be atom A forming a covalent bond with atom B. And if the two atoms are not the same atom, then they can have a difference in electronegativity, and as a result, there will be some degree of ionic character in this covalent bond. So let me explain a bit more. So because we introduced the term electronegativity here, so we need to define what electronegativity is first. So electronegativity is defined to be a measure of the tendency of an atom in a covalent bond to attract a bonding pair of electrons. So, right, for example, if atom A is covalently bonded to atom B, and atom A has a higher electronegativity, it will mean that atom A has a higher tendency in a covalent bond to attract a bonding pair of electrons. It means that, right, the shared pair of electrons will be closer towards A as compared to B. However, if you look at another case whereby A is bonded in a covalent bond to another A, right, because they're the same atom, they cannot have a difference in electronegativity. And as a result, right, the shared pair of electrons will be right in the middle, whereby there is no difference in electronegativity between the two atoms, which is exactly the same. However, if A has higher electronegativity, it would mean that the shared pair of electrons is closer towards A. And as a result, right, okay, like if it's right in the middle, then A does not lose any electrons because like each one of them still own half of the pair of the electrons. However, if the shared pair of electrons is closer towards A, it will mean that A actually has a greater share of this shared pair of electrons, and as a result, right, A would gain a small partial negative charge and B would gain a small partial positive charge. It's as if B lost some electrons because of the fact that this shared pair is closer towards A. Okay, so like I would like to mention again, this delta, it means it's a partial negative charge because it's not a complete loss of a full electron by B, and it's not a complete gain of one electron by A. So it's a partial negative charge and a partial positive charge. And this happens when A and B is in a covalent bond, whereby there's a difference in electronegativity between the two atoms. Okay, so the more electronegative element will pull the electrons of the covalent bond towards itself, as in this case, and it will acquire a small negative charge, which is indicated by this delta minus, while the other atom will acquire a small positive charge, which is indicated by this delta plus. Okay, so that's why in a covalent bond, whereby two atoms have different electronegativities, there will also be some ionic character because one atom will gain a partial negative charge and the other atom will gain a partial positive charge. So if we were to look at this molecule called water, OH2, so by right, the shared pair of electrons should be right in the middle, but oxygen is much, much more electronegative than hydrogen. So the shared pair of electrons will be much closer towards oxygen as compared to water. Okay, and hence this is called a polar bond. And the way that we indicate the polar bond is to draw an arrow towards the direction whereby the shared pair of electrons is being put. So the bond polarity of this bond is in this direction, while the bond polarity of this bond is in this direction. Okay, if heteronuclear covalent compounds contain atoms with difference in electronegativity, heteronuclear covalent compounds means that the compound is made up of different types of atoms. So in this case, it's true, it's different type of atoms because it's between oxygen and hydrogen. So they will result in covalent bonds in ionic character and they will result in polar bonds. And I remind you again, we draw the arrow towards the more electronegative element along the bond. And if we want to talk about the overall bond, the overall polarity of the molecule, we would add up this vector to this vector. So like those of you are not familiar with addition of vectors, right? What you do is that you place this vector like this, and then you put the second vector continuing on from the first one. And the result, this is the sum of the two vectors. So this is the sum of the bond polarity vectors, if you want to call it that way, polarity vectors. And this sum is equals to the overall molecule polarity. Okay, the overall polarity of the molecule. If the vector that after you add up all the bond vectors, you don't get a zero vector, it will mean that that molecule is overall polar and it actually has a polarity. Okay, so one thing I'd like to point out here is that when we draw the arrow, we always draw it in the way towards the direction whereby the electrons are being put. So it will be this direction because the electrons are being put along this bond in this direction from H to O. However, in physics, right, like when you have a delta plus and delta minus, in fact, the bond polarity is actually drawn in the opposite direction in the sense that it's from minus to plus. But in chemistry, right, it's actually from plus to minus in the opposite direction. So I just like to point this out in case there are physics students out there that get confused in the sense that why is it that in physics we define the bond polar, like if you have a dipole and you want to define the bond, the dipole, you will always draw an arrow from minus to plus, but in chemistry it's from plus to minus. It's just a matter of convention. Okay. However, if in this case, right, like hydrogen, H and H, they are the same type of atom, so the electronegativity is exactly the same for the two atoms, and hence the shared pair of electrons is right in the middle, and neither of the atoms will gain a partial plus or partial minus. So in this case, whereby homonuclear covalent compounds, homonuclear means that all the atoms are the same type, whereby they contain atoms with no difference in electronegativity, they are pure covalent bonds. Okay, so there is no ionic character in homonuclear covalent compounds. Okay, so basically, ionic compounds, there will always be covalent character because once the metal loses the electrons, it will form a positively charged cation and it will start to pull back the electron cloud of the anion. Covalent bonds, if they are homonuclear, it's really a pure covalent bond with no ionic character. Only when it's heteronuclear covalent compounds, then it will lead to bond polarity. Okay, so there is no such thing as a pure ionic bond, but there's a such thing as a pure covalent bond, whereby the atoms are homonuclear types of covalent compounds. Okay, so this is a table showing the electronegativity. So since electronegativity is defined as the tendency to attract a shared pair of electrons, the higher the number, the higher the tendency for that atom to attract a shared pair of electrons. So of course, you don't have to remember all the numbers here, but there are a few things that I'd like to point out. So one is that when you go across the period, right, the electronegativity increases. We will learn more about the reasoning why when we study periodic table, but actually I've really learned this in atomic structure. So on the part of effective nuclear charge, if you were to go back and look at the lectures and you can revisit effective nuclear charge and you can think for yourself how you can apply effective nuclear charge to understand why is it that across the period the electronegativity increases. It's actually very similar to ionization energies. Moreover, when you go down the group, the electronegativity actually decreases. Okay, decreases. Okay, and one more thing that we would like to know is that fluorine is the most, fluorine is the most electronegative element in the whole periodic table, followed by oxygen, followed by nitrogen. Okay, so you need to know FON in that order, and then you also need to know that electronegativity increases across the period and decreases down the group. Okay, so for example, this is something that I already covered in the previous part. So for example, if you've got a molecule of water like this, so oxygen is more electronegative than hydrogen, so we'll draw a bond dipole in the direction towards the more electronegative element. And the overall dipole of the molecule is when we add up these two vectors. So you add up these two vectors, and then for this water molecule, this is the overall dipole of the molecule. Okay, so this is important when we study the interactions between molecules, and we can use this to decide what type of interactions happens between different type of covalent molecules, and we can use this to deduce whether their melting point is expected to be higher or lower than each different type of covalent molecules. We'll cover more of that in the next chapter, but for now, we just need to know, based on the shape and based on drawing the bond vectors, we add them up to decide whether that molecule has an overall dipole or not. Okay, so the dipole moment of a molecule is the vector sum of all the individual dipole moments of the covalent bonds in the molecule. If the molecules with polarized bonds and it's not symmetrical, that means the bond vectors will not cancel out. When you add them up, you will get a non-zero vector, and that non-zero vector is basically the dipole moment of the overall overall dipole moment of the molecule, and the molecule will be polar. However, for molecules with no dipole moment, they are non-polar. So basically what it means is this. For a homonuclear covalent compound, there is no bond dipole. So if there's no bond dipole, when you add up all the bond dipoles, you will necessarily get a zero vector. If it's a zero vector, it will mean that molecule doesn't have an overall dipole moment and it will be non-polar. So as an example for this is like HH bond. There is no bond dipole, and therefore when you add up all the bond dipoles, you get a zero dipole moment. And since it has zero dipole moment, this is a non-polar molecule. On the other hand, you can have another case such as BF3, right? BF3 is a different case because BF3, fluorine is more electronegative than boron, which means that you draw three arrows, which is the three bond vectors. However, when you add these three bond vectors, right, you will go back to the starting point, and this will be actually a zero vector, which means that BF3, although there are polar bonds, the overall molecule has no dipole moment, and this molecule is also non-polar. Okay, so there are two cases whereby a molecule can be non-polar. One is that there are no polar bonds at all, and the second one is that there are polar bonds, but when you add up the individual dipole moments of all the bond vectors, you get a zero vector. And this will then also result in the molecule being a non-polar molecule, because overall this molecule doesn't have a net dipole moment. Okay, a few examples. So for example, HCl, we will draw chlorine is more electronegative than hydrogen, so we'll draw an arrow in this direction. This bond vector will not cancel out with anything when you add to other bond vectors. In fact, this is the only one. So this is a polar molecule. NH3. So anyway, the important thing is also that you need to combine with the shape of the molecule. So for example, NH3, right, is in the shape of trigonal pyramidal. So when you draw the bond vectors from along the N and H, and you add these three vectors up, you will get an overall dipole moment that's pointing in the upward direction. However, right, if you mistakenly think that NH3 was in a trigonal planar shape, then when you draw the bond vectors like this, right, it will actually cancel. This will result in a zero net dipole moment, and you will conclude that ammonia is not a polar molecule. The reason that you will get it wrong is if you got the shape wrong. Okay, so in order to get this correct, you need to first use BS-EPR theory to determine the shape of the molecule. Then step 2 is to draw arrows along the bond vectors. Step 3 is to add vectorially the bond vectors and see whether you get a net zero vector or not. If you do not get a net zero vector, then the molecule is polar. If you get a net zero vector, then the molecule is non-polar. Okay, so BF3 is an example that I went through just now. If you draw an arrow towards fluorine and then you add these three vectors, you get a zero vector, and therefore it's non-polar. Basically, if the molecule is symmetrical, right, then when you add up the bond vectors, you are going to get a zero vector. Okay, for those of you that are not familiar with the addition of vectors, if the molecule is symmetrical, then when you add up the bond vectors, you're going to get a zero vector. Like this molecule is tetrahedral, you will draw arrows towards chlorine because chlorine is more electronegative than carbon. And when you add up these four bond vectors, you're going to get a zero vector because of the fact that this is a symmetrical molecule. Okay, so although there are bond dipoles, but they add up to be zero, so it's a non-polar molecule. For this case, although it's in a tetrahedral shape, there's only one arrow. For all purposes, when we are considering bond vectors, there is no electronegativity difference between carbon and hydrogen. Okay, this is for the purpose of this determining bond polarity. No electronegativity difference between carbon and hydrogen. If you were to go back the actual numbers, right, carbon is 2.55 and hydrogen is 2.2. So we consider it to be quite similar. So we consider that there is not much bond dipole between C and H. Okay, so the only bond vector is along CCl. So this has a net dipole moment. The molecule has a overall net dipole moment, and this molecule, CH3Cl, is a polar molecule. Okay, so that's for all the content from these two learning outcomes, and we will look at two past year A-level questions that test on these two learning outcomes. The first of which is November 2007, paper 1, question 6. Which molecule has the largest dipole? So if you look at this molecule, for C and H, there is no net dipole moment. Sorry, along C and H, there's no dipole because they have the same electronegativity difference. Later, you also learn from organic chemistry that CH3 is an electron donating group, which means that there will actually be a bond vector along this, in this direction. Okay, so if you were to add up these two bond vectors, you will get a overall dipole moment in this direction, and this molecule will be polar, and it will be in this direction. For this case, oxygen is more electronegative than carbon, so this one has a bond vector in this direction, and this one has a bond vector in this direction, and this one in this direction. If you add this, you're going to get this, but on top of this, you have to add this one, which means that this bond vector is going to be longer than this. Okay, because you are adding this two, which is also present in here, but to this vector. So you're going to get a resultant longer vector. Okay, so this molecule is definitely has a larger dipole moment than the molecule in A, and this will have a larger dipole than A. This molecule, you draw a bond vector like this, and then you will draw a bond vector like this and like this. Okay, because chlorine is more electronegative than carbon. If you add the chlorine and these two bond vectors, you're going to get a vector like this, and then this is in the opposite direction to this, so it will cancel. However, the oxygen is more electronegative. It will mean that you will get an overall bond vector in this direction. However, this molecule will be polar, but this one will be shorter as compared to this one. Because the two chlorines is in the opposite direction, it will cancel part of the bond dipole between the carbon and the oxygen. Okay, for this case, you draw a bond vector in this one dipole in this direction, this two is going to cancel. You will draw one like this, and you draw one like this, and this two is going to cancel. So everything cancels. So this one will result in a zero net dipole. And if it has a zero net dipole moment, this molecule is actually non-polar. Okay, so the molecule that has the largest dipole is this case. Because when you add up all the bond dipoles, you will actually get an overall largest dipole. Okay, so the answer is B. For this question, November 2008, paper 1, question 31. Carbon forms double bonds with each of the group 6 elements, oxygen, sulfur, and selenium. In each case, the double bond is polar. In the molecules carbon dioxide, carbonyl sulfide, and carbonyl selenide, the polarities of these double bonds do not necessarily cancel. Okay, so the overall polarity of the molecule CO2, so you need to figure out the shape first. So it's like this. Look at this molecule, right? There are actually polar bonds because oxygen is more electronegative than carbon. So you will draw one in this. However, when you add these two vectors up, you get a zero bond vector. And that's the reason why the overall polarity of carbon dioxide is zero. If you look at COS, okay, anyway, remember like the most electronegative element in the periodic table is fluorine, followed by oxygen, which means that there will be a bond vector towards oxygen, and there will also be a bond vector towards sulfur. But the thing is that for the sulfur one, it will be shorter than oxygen, which means that there is an overall dipole moment towards the right. Okay, and this molecule is actually polar, which is indicated the overall polarity is 0.71. On the other hand, CO, Se, right? So again, this one is in this direction, but because selenium is lower down in the group as compared to sulfur, So the electronegativity of selenium is actually smaller than that of sulfur, which means that this bond vector is going to be even smaller. So if you add these two up, you're going to get an overall longer dipole in this case. And that's the reason why for this molecule COSE, the overall polarity is 0.73, which is the largest among the three. Okay, so which factors could account for these observations? The C double bond S is more polar than the CSE bond. This is correct because like this one is actually longer because of the fact that sulfur is above selenium in the periodic table. And when you add these two, you get an overall larger dipole moment. And that's the, sorry, you'll get, because this is actually longer, so when you add these two up, you're going to get an overall shorter dipole moment. And that's the reason why this is actually smaller than that of COSE. So like option 1 is true. Option 2, the C double bond O is more polar than the C double bond S bond. This is also true because of the fact that oxygen is more electronegative than sulfur, because oxygen is higher in the group as compared to sulfur. Okay, this is the wrong answer because the C double bond Se bond is actually less polar than that of the C double bond O, because C double bond, the oxygen is actually more electronegative than the selenium, and hence the C double bond O is actually more polar than the C double bond Se bond. Okay, so options 1 and 2 is correct, while 3 is wrong. So basically the answer will be B for this question. Okay, so I went through 2 questions and I hope that you now know how to apply the concept of the VSEPR theory to first determine the shape, then to be able to draw arrows along the bonds of different electronegativities. The arrow will point towards the more electronegative element, that will be the bond dipole vector. And then you add up all the bond dipole vectors to get the overall dipole of the molecule. If it's the overall 0 vector, then the overall polarity will be 0. If the overall vector is non-zero, then the molecule will have an overall dipole moment and the molecule will be overall polar. Okay, we will apply this to understanding melting points and boiling points of different types of covalent compounds in the next section. Okay, so again, the learning outcome F, to be able to explain and deduce bond polarity using the concept of electronegativity, and to deduce the polarity of a molecule using bond polarity and the molecular shape. So hopefully you have taken away how to do this part, these 2 learning outcomes of the topic, from the topic of chemical bonding from the JCH2 chemistry syllabus. If you like the video, just hit the like and subscribe button, and I will see you again for the next video, whereby we look at the next few learning outcomes from the same topic. So thanks for tuning in and see you again.